And we're on. Good afternoon, everybody. It's day 22. Welcome along to Lockdown Learning. Day number 22, as I already said. And I've been trying today to do a couple of things, just cosmetically. So one is I'm trying to get to know my encoding software better. So hopefully we'll see some probably quite subtle improvements in the quality of my or the professionalism of my streaming. It may be a little bit unlikely, but we're going to give it a shot. So there's that, and the other thing is trying to give things a little bit of a facelift. So I'm aware that this this picture which I threw together to stick up as a over the top of my videos at the beginning, which hasn't really changed. Well, it hasn't changed at all. Let's face it, all the way along, and it's just some text on a plain background. So I'm gonna unveil my new look. Some text on a not quite so plain background. Yay! So. All of my videos look the same. When you look at the channel and you look at the previews, they all look the same because they've all got the same picture. So they're still going to look the same, but at least I'm going to have the number on them, and that's what I'm going to do from now on. So yes, go me, brand new look. So that's my housekeeping news for today. Okay, from yesterday, as you will remember, we started to introduce R. So we installed R and RStudio, and got ourselves up and running. So we've hopefully all got working R installations on our local computers, and we started to explore the way that R works. Okay, so we started to run some commands. We started with some simple arithmetic, and we kind of went on from there. And so today we're going to continue that exploration in R. So we will we'll have a look at some other features of R and see where that takes us. Incidentally, the background for this picture. It looks, as some people are rightly pointing out, it does look a bit matrixy. You can replicate this effect yourself in your virtual machine by installing a particular program. So I've installed it in my virtual machine. So here we go. Here's my VM. And I installed this program. It's called CMatrix. And if you install it using apt, so sudo apt install CMatrix, and then hit enter, then you too can feel like you're living in the matrix. So I just thought I'd draw attention to that. Some whimsy for once in the Unix world. Okay, so that's that. Right, back to R. Okay, so here's RStudio, and the first thing that I'm going to do, and I'm not going to suggest that you do this, but I'm doing this essentially for display purposes. I'm going to reorganize the arrangement of my panels in RStudio a little bit, just to make it easier for me to fit more stuff on the screen, basically. So I'm just going to go to Tools and Global Options, and then Pane Layout, and I'm going to leave my source on the left, but I'm going to put my console on the right. Essentially, that's my rearrangement. So I'm going to have source on the left, console on the right, and then I've got environment, history, and connections down bottom left rather than top right. And then so I've just swapped the console and the environment around. And the reason for that is, oh, I need to restart RStudio. That's annoying. Okay, so I'll do that. Let me just do that while I do that. Don't save. Okay, so I'll just restart RStudio to let that change take effect. And wait while it comes back up properly. There we go. Right. Okay. So housekeeping, and there we are. So that's me back, and the reason I've done that is just so that I can have my console, my script take up as much space as possible, and my console and plots take up as much space as possible on my screen without it. So you can actually see what I'm doing, basically. So hopefully this will enable me to have as informative a screen for you as possible. For YouTubing purposes. So I've got my source on the left and my console on the right, which will, if you don't have that, that's absolutely fine. I wouldn't expect you to rearrange your screen to look like mine. Just keep it the way that it is, because obviously you can have everything maximized and have lots of screen real estate, hopefully, for everything. Okay, so where are we going to begin today? So yesterday we didn't get very far, really. We looked at R as effectively as a calculator. So we looked at doing simple arithmetic in R. There's that again. Let's get rid of that. The reason that error message is cropping up the first time I run a command is just the fact that my R installation is really old. It's been kicking around on this computer since I got the computer. So let's try not to let that alarm ourselves. Okay, so there we are. R doing arithmetic. The thing I should note is R honours the expected order of operations. So if you do slightly more complicated arithmetic, R does the multiplication before the division. Multiply and divide have higher precedence than addition and subtraction. So this is the same as doing 2 plus 5 times 7 in brackets. Okay, so this is effectively the same operation. So the results of this is not going to be 49, it's going to be 37. Okay, that's useful. Oh, by the way, there I'm using a hash character, the same as we did in Bash. The hash character is for comments, and everything after the hash is ignored. So that means that on that particular line that I executed there, only the arithmetic before the hash got executed. Everything from the hash onwards was ignored by R. And that's because that's treated as a comment, because it is a comment. So that's true of an awful lot of programming languages. Most, if not all, programming languages have some way of making comments. The hash character is quite often the comment character, and so here we're just making use of that, just to add some explanation to our text, to our line of code. So we mostly covered that yesterday. And then at the very end, just to show you the plotting functionality, the way that RStudio handles plots, I introduced you to our very first function in R, which was plot. So we produced a plot using the plot function. So plot, I did 1 to 10, comma 1 to 10. and that produces a plot. So that's a function, and that's kind of where I wanted to pick up today, is to talk a little bit more about functions, what they are in R, and how they're used and what they do. So, okay, so functions. So functions can essentially be considered to be like mini programs that are part of the R programming language. So, like we used programs at the command line to do particular functions like cat and grep and so on and so forth, we have functions in R that enable us to do similar things with data within R. So either with data that we input as part of the function, the call to the function, it's called a function call, or as data that we've got stored in our environment. So the other thing that we did yesterday was look at variable assignments. So by typing in x equals something, we set a variable in our environment. So just to pull up the environment to show you that x equals 10 has been set in my environment. So you can also use functions with the data that you've got stored in your environment as well. So functions are really a really useful way, and functions are basically the ins and outs of how you do pretty much everything in R. These kind of literal calculations that we've been doing so far are useful but really limited, and it's really by using and writing to a certain extent functions that we'll be doing meaningful things with R. So we've already seen plot as an example of a function. Plot's perhaps not the simplest place to start, so let's step back a bit and think about some slightly simpler functions. So, for example, the log function. Right? So we call a function in R. So functions. So we call a function in R by typing the name of it, and I'll just note at this point. This is what's popped up here on the screen. This is RStudio being helpful. So RStudio, like our command line, has methods for completion. So at the command line, we press tab to complete our current command or our current file path or whatever it is we're in the middle of typing. RStudio also has a completion interface, and this is what's happened here when I've started to type the name of a function. This is my completion interface, and this has popped up everything in my current environment which begins with the word log. So we've got the function log, which is the function I'm trying to show you, but lots of other things besides, as well as this this class, I think this is. We don't want to worry too much about that right now. But if I click on one of these, then it will complete it for me. And then I get another little tooltip pop up, which gives me some help on how to use this function. So it gives me a little vignette of the arguments that I need to use. So functions take arguments within the brackets. Okay, so inside the brackets, we put a comma-separated list of arguments. So the simplest way of using the log function is just to provide it with a single argument, a single numerical argument, and log then this is then log's default mode of operation. It will find me the natural logarithm, or logarithm to the base e, of the number in the brackets. So log brackets 10 will find me the natural logarithm of 10, which is 2.302. And again, the result there being printed out in my console, because I've not assigned it to any sort of variable or anything. So all I'm doing is essentially asking R to tell me what the result is at the console here. So that's the simplest way. Log also has you've got a second argument for log, which is the base that you want the logarithm returned in. So by default, as I said, you get it to base e, the natural logarithm, but you could ask for the logarithm in base 2, for instance, and that would give me the log in base 2 of 10, which is 3.3. Or you could ask for the log in base 10 of 10, which is 1, obviously. That's how we kind of configure our function call. So we make a call to the function by using the name of it followed by round brackets, and then you put your arguments for that function in the brackets. And this is generically how we use functions in R. If you want to know what the incidentally, for those last two there, you may have noticed it when the little pop-up came up, but there are actually functions which are shortcuts for these two logs. So rather than doing log comma base 2, you can just call the function log2, and that will find you the base 2 logarithm of the given argument, and the same for log 10. But that's just a note there for those things. That's the generic idea of how to call functions in R. Obviously, most of the time, and this is true for me as much as it will be for you, most of the time you won't know when you call the function, so you won't know when you start to write your function call what the arguments that are actually available are. So you need to be able to look at a help file or a man page or something similar for that function, and R has that functionality. So if you want to understand what the arguments are for a particular function, then you can look at the help file for that function, and you do that with the question mark operator. So question mark and then the name of a function will open in RStudio. Will open the help file for that function in the help pane, which you can see down here in the bottom right hand corner. So this will open the help for log, so it's opened up my help pane here in the bottom right. Let's just let that take over that side of the screen. And this is the help file for the log function. So you get a description of what the function tries to do, quite especially for functions in the base package. So base is the package that this log function belongs in. So base is essentially the core of the R programming language. So whenever you install, you get a description, and here R is grouping together a set of related functions. So not just log, but log 10, log 2 is here as well, and the exp function, which exp is the kind of opposite of log. So whereas log by default will find the natural logarithm of a number, exp will compute the exponential, so we'll raise e to the power of the argument. This is the help, and it describes our two arguments. So the two arguments for log are x and base, and x is a numeric, essentially, so a number, and b is also a number. So base, sorry, is also a number. So that's our description. These are our arguments, sort of describing these different functions that are all related to one another. And then here's a description of the arguments and some details about what happens and all the rest of it. So for log, this is perhaps relatively simple, but for other functions, these help files can get long and complicated. There's nothing to stop us assigning the results of a function call to a variable in the same way as we just assigned simple numbers or the results of arithmetic to a variable yesterday. So yesterday we were assigning, so like I have done here, x to a number or x to the results of some calculation. We can also assign a variable to the results of a function call. So we could assign x to the log 2 of 16, right? And we could assign y to x squared, okay? And then we could do x plus y, okay? So here, instead of assigning a simple number or the results of a calculation, we're assigning the results of a function. The result of this function is a number. So it's not returning us anything complicated. It's just R is giving us back a number here. So x there has been set to the results of the log 2 of 16, which if we look in our environment, we will see that x is 4. So x is a number. It's not been set to log 2 16 or anything like that. It's been set to the results of that function call. So 4. And then x this is the inverse operation, so raising the results of the log 2 to the power of 2, so this gets us back, that returns us to 16, and then 16 plus 4 is 20. Okay, so it's relatively well, it's nice to be able to do that, and we will obviously be exploiting the ability to save the results of running functions like this in future lessons. And hopefully what you saw there, where also when I ran line number 10 here, the x equals log 2 16, is it overwrote any value of x that was currently stored. So my x equals 10 was overruled by my x equals log 2 16. You could also do if I reused the variable, so if I did x equals log 2x, the way that R does this is it evaluates the thing on the right hand side and then sets it equal to the thing on the left hand side. So it doesn't get confused by this. It doesn't try and do this recursively until the heat death of the universe and keep log 2ing x until something breaks. This is done, this right hand side is evaluated and then is set equal to x, and the value of x will change as a result of doing this operation as well. So if we run that line, we will find that x has changed its value. It's now 2 rather than 16. And as you saw yesterday, the order of the computation in the script, when we're running individual commands like this, doesn't really matter. I could go back and I could run line 4 again, and x would be set to 10. And then if I ran line 12 again, even though it comes after line 10 where the value of x changes, it would still use the current value of x, which would be x equals 10. So in the case of what we're doing at the moment, the order of things in the script doesn't really affect the results that we're seeing at the console. It's the order that we run the commands in that matters. The order of the script matters if you run the whole script as a kind of as a cohesive object, which we will be doing at some point in the future. But if you're just running it line by line, then the order you execute the lines in matters, not the order the lines are written in. But it makes sense to write the lines of code in the order that you're expecting to execute them in. Okay, so so far we have only dealt with numerical data. Okay, so we've only messed about so far with numbers. Okay, so we've done arithmetic and everything, and fairly straightforward operations, but it's all been numerical. But R can handle different types of data quite happily. So we don't have to just work with numbers. We can work with other types of value as well. The simplest data types that R has are what are called doubles, and doubles are numbers. So that's what we've been working with so far. Is the data type called double, and there are historical computational reasons for why it's called a double. The other two major simple data types are character, so that is essentially a string as we understand it in other programming languages and at the command line, and logicals, so they're the Boolean values true and false. So we can look at those data types as well. So let's do x equals 3, y equals bioinformatics, z equals false. Okay, so these are our three simplest data types that R has. So the first one, x equals 3, is a double. The second one, y, is a character, and the third is a logical. So that's a Boolean value, which can either be true or false. So true and false are written in all capitals without quotation marks, and that's how you define true and false. Numerical values, so doubles, are again written without quotation marks as numbers. So that x equals 3 there is defining a double. If I were to put this in quotes, so if I were to surround the 3 with quotation marks, this would now be a character, not a double, because we turned it into a character by surrounding it with quote marks. So quotes are always expressed. Characters are always expressed in quotes. So if I just typed the word bioinformatics here, R would look for a variable with the name bioinformatics, rather than a character, rather than you giving me a character with the value bioinformatics. Bioinformatics. Okay, so if you're thinking about characters, then you need quotes. So let's set these 3 values, and I'm just going to bring up my environment while I do this on screen. So we've already got x and y here. These lines are going to overwrite the values of x and y. Okay, so x becomes 3, y becomes the character of bioinformatics, and then z is false. Okay, and then we have functions which allow us to test the type of a particular variable. So we can test is double, is dot double, tests whether the argument, so you give is dot double is a function call, so we need brackets, and then you need an argument, and it will test whether the argument is a double or not. So if we give is dot double x, then the result that we get should be true, because double is x is a double. So if we run that, we should see true returned at the console, which we do over on the right hand side, because x is a double. Y, on the other hand, isn't a double. So is.double y will return false. Okay, but is.character y will return true. And you'll notice that these functions are returning logical values, so true and false. Okay. There are also some special data types that are used to represent certain concepts in R, and we're going to think about three of those right now, just to introduce them as concepts. So the first one, which I saw mentioned in the comments yesterday, is infinity. So R has a special data type to represent infinity. So if we do division by zero, the results of dividing by zero is infinity. So what we get back is this special data type, which is inf, which represents infinity. Okay, so inf is our first special data type. The second one is if we try to subtract infinity from infinity, then R considers this to be an invalid operation, and it gives us the result NaN, which stands for not a number. Okay, so NaN is not a number, which usually means something has gone wrong somewhere. And then the final special data type, which I can't think of an operation to produce, but the third special data type is Na, and Na denotes a missing value. So Na will quite often we'll find quite often cropping up when we've done something that produces a missing result, or if we've got a table of data that we're reading in, for instance, that have some missing observations, then you'll end up with some NAs appearing in your data at some point. We will no doubt run into NA again in the future. Okay, so there are three special data types. Okay, so there's one more thing that I wanted to talk about today. I think, depending on how long I ramble on about it, but I would imagine that this is the one other thing that we'll get time to talk about today. So far, I'm trying to introduce things gradually and kind of build things up slowly. So far we've dealt with single values. So all of our variables, all of the results of our calculations, everything that we've done so far has been working with single values. In R, these are called scalars. R's very good at working with single values. You've seen we're doing nice speedy arithmetic. It works very well for that. But for a lot of the operations that we want to do, just operating with single values would be extremely limiting. It would be it would make things very, very difficult. So R is also very good at operating with not just single values, but groups of values, sets of values, in both 1 and 2 dimensions as well. But we're going to deal to begin with just one dimension. So one dimensional set of values in R is called a vector. And vectors are at the heart of the way that R does all of its computation. So we need to know how to define sets of values, and we do it using a function. So there's a function in R that allows you to combine multiple single values into a vector, and that function is just a single character. It's the function C. Okay, so C allows you to concatenate multiple values into a vector. So we can construct a vector of numbers by passing those numbers as arguments to the C function. So there you go. There's a set of numbers. This will define a vector in R with 5 values. Okay, so if we just execute this, it will print that vector at the command line, at the console on the right hand side. So that's our vector, which has 5 values. We can set this vector to be a variable in exactly the same way as we can our single values. So we've had things like X, Y, and Z. There's no limitation, by the way, on, like, there's nothing that says that your variables have to have single letters as their names. So I've been doing X, Y, and Z so far, but we can call this my first vector. Okay, and this is a perfectly valid variable name. So let's run that line of code and then have a quick look at our environment. You can see up in my values has popped up my first vector, which is this is telling me it's a numerical vector of length 5. So it's got elements 1 to 5, and these are the values that are inside that vector. Your variable names can contain uppercase and lowercase letters. They can contain underscores, they can contain dots, but they can't contain hyphens, minus signs, because that's a numeric operator. They can't contain forward slashes. They can't begin with a number or a special character. So that's a perfectly valid variable name, whereas this wouldn't be. So if I tried to set that to be a variable, sorry, my first, well, it doesn't matter, it's not a vector. So if I tried to set that to be a variable, it would fail because what it's actually trying to do is it looks for 3 variables called my, first, and vector and tries to subtract them from each other because this means subtract. Okay, so it's trying to do something, but my dot first dot vector is perfectly fine, although there's lots of people who don't like dots in variable names, which I completely understand. You could have so you could go back to this and do my first vector 1. That would be fine. That would work as a variable name. But 1 my first vector wouldn't. Okay, that wouldn't be allowed. So you've got a lot of flexibility in naming your variables, and it makes a lot of sense. Although, single letters, very short variable names, they're very quick to type, and if you're using that variable a lot, it can make some sense if you keep the name of your variable short. But for reproducibility and for your own sanity, for future use sanity anyway, it makes a lot of sense to give your variables meaningful names. So names which in some way represent what they are. So that when you come back to read this code in 6 months' time, you kind of understand the purpose of your vectors, of your variables, and that's true for comments as well. Comments are there to help you understand the code that you write. Don't expect that code is self-documenting, because as our code gets more complicated, it also gets more complicated to try and figure out what particular lines of code do. So a comment which expresses the intent of the following line of code can be extremely helpful to future you or to anybody else who wants to read this code in the future. So it's really important to kind of try and make your code self-documenting by helping yourself out in that regard. Okay, so to move on, my first vector here is a vector of doubles. Okay, so for my first vector is.double my first, and this is where we get tab completion as well. So I've got a long variable name now. So RStudio gives me the ability to use tab completion. So I could start typing my first vector and press tab, and it completed it for me, just like we can at the command line. Okay, so is.double my first vector. It's a vector of doubles, so it is true that this is even though it's a vector, it's also a double because it's a vector of doubles. It's also a vector, is.vector. My first vector will also return true because it's also a vector. So this hints at another property of vectors, which is that all of the values within a vector all have to be of the same data type. So here I've got a vector of doubles, and they're all doubles, so that's fine. So that works very well. So for my second vector, I can make a vector of characters, right? So vector of characters. Okay, so that they're all the same type because these are all characters because they're all surrounded by quote marks. So if we create this vector, then is.character for my second vector will return true because everything in that vector is a character. Okay, so those two vectors that I've created so far obey this rule that everything within a vector has to have the same type. So what happens if we try to create a vector which has different types in it? So how about in my third vector, we put in, okay, so we're going to make a vector, so we're using the C function. So we put in two doubles and two characters. So how does this obey the rule that everything in the vector has to be the same type? Well, it doesn't obey that rule. Okay, it isn't the case that everything in this vector is the same type because we've got two doubles and two characters. So the question that follows from that is then, well, what do we think R will do? Will R say, I don't like this, I don't want to do it? Or will R silently try and fix the problem for itself? The answer to that is the second one. So if we run this line of code, we don't get an error. R isn't saying not everything in this vector is the same type, so I don't want to create this vector. It creates the vector anyway. So the question now is, what type is the vector? So if we've added two doubles and two characters into the vector, what do we end up with a vector of doubles, or do we end up with a vector of characters? And the answer to that is we end up with my third vector. We end up with not a vector of doubles because A and B can't be turned into numbers by R, not very easily anyway. Instead, we have actually ended up with a vector of characters. So is character my third vector? So you see, when I just had my, and I pressed tab there, I got all of the options that begin with my underscore. So that's my three vectors that I've created so far. And then I can just use the arrows on my keyboard to scroll down to the third one and then hit enter to select it. Or you can just click it with the mouse. So is character for my third vector will return true. Because what's happened when we've created this vector is A and B can't be turned into numbers, but into doubles, but 2 and 3 can be turned into characters. So that's what's happened, is it's turned 2 and 3 into characters. So you see, if I print out the vector at the console, you'll see 2 and 3 are now surrounded by quotes, which means they're characters. So it's converted the two doubles into characters, and R has a hierarchy for doing this. So in a mixed vector, logicals will be turned into doubles, and doubles will be turned into characters. So if you do a mixed vector of, I'm just going to do this at the console. So if you do a mixed vector of logicals and doubles, R will turn the logicals into doubles. So your basic order of things is logical is less than, double is less than character. Okay, so if I run this, the resulting vector has turned the logicals into numbers. So trues are turned into ones and falses are turned into zeros. Okay, so we get 1, 0, 3, 4 because the logicals have been turned into doubles. If we add to this vector, and this is another feature of RStudio. Actually, this is a feature of the R console generally, but the R console has a history just like the command line. So if I press the up arrow on my keyboard, I can go back to the last commands that I executed at the console. So I've just pressed the up arrow there on my keyboard. So if I add a character to this, sorry, I'm mashing my keyboard today. So if I add a character, even though that character can be cast to a double, it can be turned into a double, it's still a character. And what will happen is everything here, I'm pretty sure anyway, I've not actually tested this, but everything will be turned into a character because of that one character that we've added in. So yes, that is what's happened. So instead of the logicals being turned into numbers, into doubles, what's happened here is everything has been turned into a character. So the true and the false and the doubles that were there before have all been turned into characters. So R is keen to create your data for you, but it will also change your data types quite happily if you've got mixed data types in a vector. That's useful information. Okay, so a couple more things with vectors before we finish today. We can create vectors of doubles really easily using the seek function. So seek will create a vector of doubles from the first number to the second number. Okay, so seek 1, 6, so 2 arguments, 1 and 6. This will create a vector of doubles going up in ones from 1 to 6. Okay, so 1, 2, 3, 4, 5, 6. Seek is configurable, so let's get the help for seek. There we go. Seek. There we go. From, so our main arguments are from, to, and by. And so by default, from is 1, to is 1, and by is also 1, I think. So so we could do seek 1, 6, and then by equals 2. So that will go up in twos. So the resulting vector, instead of being 1, 2, 3, 4, 5, 6, will be 1, 3, 5, because it will go up in twos rather than in ones. You could also do it. You could also use seek to go the other way. So we could go from 6 to 1 by -1, and that will go from 6 down to 1. Okay, so seek is quite useful for creating vectors of doubles. You can also use colon for the same effect. So 1:6. We looked at this yesterday when we first ran the plot command. 1:6 will also produce a vector of doubles from 1 to 6. You can get help on this by doing. You have to put the colon in quotes, but you can still get help on it. So this is the colon operator from :2 a colon b. So it will return you your sequence of integers between the two. So, but if I'm not sure what happens if we go 6:1, let's try it. I've never done it before. There you go. It does give you the reverse sequence. So 6:1 gives you 6, 5, 4, 3, 2, 1, whereas 1:6 gives you 1, 2, 3, 4, 5, 6. relatively useful. But you can't go in steps of 2 with the colon. You can only go in steps of 1. Okay. So then the final thing that I want to talk about is doing operations with vectors. So we can do arithmetic with vectors in the same way as we can with single numbers. So if we have so my vec equals 1, 2, 3, 5, 8. Okay, so just a vector of 5 numbers, and then my vec2 equals 6, 9, 18. Also a vector of 5 numbers, so 2 vectors, both of length 5. So let's create them. So they're now in my environment. Just pop my environment up. You'll see that they've appeared in there. I should also say at this point, useful ways of operating with vectors. There's a function called length, which takes a vector as an argument and tells you how long it is. For a vector of numbers, there's a function called sum, which takes a vector and adds them all up. And there's mean, which will tell you the average of that vector, and so on and so on. There's lots of these really useful functions for working with vectors. But I was talking about vector arithmetic. So we can both of these have 5 elements in them. We can add them up. So my vec plus my vec2 will add vector 1 to vector 2. So what happens is element 1 gets added to element 1, element 2 gets added to element 2, 3 gets added to 3, and 4 gets added to 4, and so on. So the results of this is the results of adding the first elements together, the second elements together, and so on all the way to the end. So we can do arithmetic with vectors like this. We can, as well as doing addition, we can do multiplication, has the same effect. So the first 2 elements are multiplied together, the second 2 elements are multiplied together, and so on. So we get another vector of length 5 out of the end of that process. The one thing I just wanted to draw attention to here is what happens if these 2 vectors are not the same length. Okay, so what happens if my vec and my vec2 are different lengths? Okay, so in this case, when we run that, my vec and my vec2 are now different lengths. They're not the same anymore, which means that the arithmetic is not as simple as just adding element 1 to element 1, element 2 to element 2. We would do that for the first 2, but what happens when we get to element 3 of my vec2? What gets added to that? Because there is no element 3 in my vec here. So the answer is that the shorter vector gets recycled. So for the third sum here, the shorter vector goes back to the beginning. So what we'll do is we will add element 1 to element 1, element 2 to element 2, and then we'll add element 1 to element 3, and element 2 to element 4, because we will recycle the shorter vector. So again, you can see that in the results here. So we've got 8 plus 2, and 11 plus 3, and then 8 plus 5, and 11 plus 7. And that's our length 4 vector that results. So when you do this arithmetic with 2 vectors of differing length, your result will always be the same length as your longest vector, and the shorter vector will be recycled to complete the arithmetic. So that's quite an important thing to note, because that's a really important feature of vectors. Okay, with that today I'm going to finish. So hopefully if you've got if you do have R&R Studio installed, which hopefully most of you do by now, you've been able to follow along with me and see these operations for yourself as we've been going. I realised that as with introducing the command line, we're going relatively slowly at the moment, but we're going to build this up to more complicated things really quite quickly. It won't take us that long to really get going with sort of more complicated operations in R. So we're going to leave it there for today. I'll introduce some more things tomorrow. I think tomorrow will again be these kind of basics that we'll be working with tomorrow, and then it may get a little bit more complicated next week. Okay, so thanks everybody for tuning in for number 22, and come back tomorrow for number 23, and for Friday. It's the end of the week already. This week seems to have gone really quickly for me anyway. I don't know about you guys, but it seems to have been a quick week. So I'll see you tomorrow. Thanks for tuning in. Keep safe, stay well. See you tomorrow. Bye, everybody.